Okay.
That's great. Okay, thank you very much.
Thank you very much. So first of all, my apologies for not being able to be there in person. I was really looking forward to going up to Cambridge, but for family reasons, I need to stay down here, I'm afraid. So I'm sorry to be missing out on all the conversations over coffee. So I was asked to give a presentation on what the magnetometer observations from the Cassini spacecraft told us about the interior of Saturn. And so I'm really going to describe those observations to you. Hao gave a rather nice introduction for me. Essentially, Saturn's planetary field is unique and rather surprising with its extremely small dipole tilt. And really this view that you can see here shows an impression of the end of mission data where we went really close to the planet. And this gave us a unique opportunity to explore the magnetic field and the dynamo. But the observations we made, even though we were really close, were complicated somewhat by some of the external fields that we saw. And so it took us a bit of work to be able to really tease out the signal that was coming from the interior. So I just want to, I'm trying to move on. Let's see if I can. Oh, I can't seem to move on to the next slide. Hold on a second. No. Let me have a look. Okay, there we go. Fantastic. Thank you. Okay, so I thought it would be a good idea to maybe start with a little bit of history of the, well, first discovery of Saturn's field was made back in the Pioneer days. The Pioneer 11 spacecraft flew past Saturn. And not only that, but I've also shown the Voyager 1 and 2 data as well. So it was Pioneer 11 that made the first in situ observations of the field. But what you can see from the data that I've shown there, which is the magnitude of the field for all three of those flybys, is what they revealed is that Saturn has a very dipole dominant internal field, magnitude of order 20,000 nanotesla. And it was shown in those days to be highly symmetric with respect to the spin axis. And back in the late 70s, early 80s, it was a less than 1 degree dipole tilt that was actually measured. And the data that's shown there is from papers by Smith and Kearney. In addition to those observations, what was found was that there was very early signs of these planetary period oscillations, which are seen not only in the magnetic field, but also in radio wave and energetic particle data. So in the top right here, let me move my mouse, is showing you some radio wave data, which essentially shows a peak at the northern planetary period oscillation period, and bottom right, you see some data, some energetic particle, ions and electron data, which again is showing you this clear planetary period oscillation in the data. And then on the left was some work that was done by a PhD student of mine, looking at not only Pioneer data, but the Voyager data as well. But this plot here shows you data from Pioneer 11. What he did is he went back to the mag data. He subtracted the internal planetary field away, and then he projected what was left on top of the trajectory of the spacecraft. And you can see going along the Pioneer 11 trajectory, again, you can see this planetary period oscillation that is clearly seen in the data. So there was clearly something that was seen in the data, which was a surprise, because with a very small tilt, you wouldn't expect to see any evidence of the planetary period in the data in the magnetosphere itself. If we now move forward to the Cassini era, again, we found that these planetary period oscillations seem to fill the magnetosphere, seen in all the fields and particles data. So looking at this plot here, we've got radio wave data in the top, we've got energetic particle data in the second panel, and then we've got the different components of the magnetic field once we've subtracted the internal field away, and the magnitude of the field down below. And this is data which was taken quite early on in 2005 from the 17th orbit around Saturn. And the question always was, what could be the source of this oscillation that we could see, since we knew that the internal field seemed to be extremely axisymmetric. So this here is looking at planetary period oscillations, which were observed by Voyager, Ulysses, and Cassini. It's quite a busy plot, but what we have here is this data plotted over about 35 years. So it's more than one Saturn year. The top panel is showing the planetocentric latitude of the sun at Saturn. So essentially what it's doing for us is it's showing us the changing seasons. In the panel below, you have both the northern and the southern planetary period oscillation periods being shown in blue and red respectively. And then the Ulysses period is shown in purple because since Ulysses was on its way to a polar orbit around the sun, it wasn't close enough to Saturn for us to be able to tell what the hemisphere of origin was. So that's why those are shown in purple. The dots are the SKR, or the radio wave data, and the solid lines are coming from the magnetometer. And what you can see is that both the northern and the southern periods are showing a strong seasonal dependence. And these northern and southern periods are converging across vernal equinox, not only in 2009, but they are with values which were close to those which were observed by Voyager one Saturn year earlier. And then following the vernal equinox, the periods remained close for a time, and then they began to diverge again. And so it seemed to be clear that these PPOs that we were seeing were not coming from the interior, but were more likely coming from something that was happening in the atmosphere at Saturn. So if we have a look at what the Cassini observations prior to the Grand Finale orbits told us, as I alluded to and Hao alluded to earlier, they placed a tight upper bound on the dipole tilt. So what we're looking at here is we're looking at magnetometer measurements that were taken inside of Enceladus orbit between 2006 and 2011. Radial component of the field is in the top panel. The north-south theta component, or the dipole component, is in the second panel, and the azimuthal component is in the bottom panel. And you can see that the azimuthal component is orders of magnitude smaller than that of the radial and the theta component. And it's that azimuthal component that will give us any non-axisymmetry. But based on these observations, we were able to resolve the axisymmetric intrinsic moments up to degree 3. And this revealed the extreme axisymmetry, and these Cassini observations even tightened the dipole tilt. It was less than 0.06 degrees. And this was work that was done by Hao Cao back in 2011. So, quick summary then. Our knowledge about the internal field of Saturn prior to the Grand Finale orbits were that the axisymmetric magnetic moments up to degree 3 were well resolved. There were actually some hints of axisymmetric degree 4 and 5 moments, because it was back when we first went into orbit, so Saturn orbit insertion from Cassini. We got close enough that we knew there was something above degree 3. It was about 100 nanotesla, which we'd not been able to model using degrees 1, 2, and 3. And so there were these hints for moments 4 and 5. There was this confirmation that the dipole tilt was very small, less than 0.06 degrees. And there were some less stringent constraints on non-axisymmetry of degree 2 and beyond. And we hoped we would find out more once we got to the end of the mission data. And some work that was done to see whether there was any secular variation showed that if there was, it was very slow. It was the order of about 1.2 nanotesla per year, so at least an order of magnitude smaller than changes that we see in the field at the Earth. So just a reminder that the observations we expect to make outside of Saturn will give us an understanding of the field that's been generated by the deep dynamo action in the interior. So moving on to the Cassini end of mission orbit. So there were 2 phases to this. So the last year of the Cassini orbit consisted of 2 different phases. So we started off, we used Titan to get us up out to the equatorial plane. And the first phase of the mission were these ring grazing orbits, or the gray orbits that you can see here. And that was about 6 months worth of orbits. And what we did is we used these ring grazing orbits to essentially inform our understanding of the B phi contribution for the grand finale orbits. We were able to make many measurements of the field line currents that were seen on these orbits, and that gave us a good understanding of the observations that we then saw on the grand finale orbits. The last 6 months of the mission, again, we used Titan to change the trajectory, and we then had 22 of these blue orbits where we went inside of the rings, just above the top of the atmosphere. And then you can also see the final orbit was shown with this orange line that you can see here. Now, one of the things that we needed to do during the grand finale orbit phase was we needed to calibrate our instrument, because in around periods, we were in range 3 for the instrument, above 10,000 nanotesla, which we hadn't been in since we flew past the Earth back in 1998. And so the instrument was not well calibrated in that high range. And so what we did is we asked the project, and they agreed to allow us to roll the spacecraft on 2 of the periapses on the grand finale orbits to allow us to be able to calibrate, because just a reminder that one of our 2 sensors on Cassini stopped working soon after we arrived at Saturn. So we only had 1 working flux gate. And for us to be able to calibrate properly, we had to insert many rolls into the trajectories that we had around Saturn, all the way through the orbital tour, to allow us to actually calibrate. The other thing that complicated things for us a bit as far as analyzing the final orbits was concerned was the fact that we needed the mission team to especially reconstruct some of the spacecraft trajectory data for us, because for some of the times around periaps, star ID suspend periods occurred. And so it took some time for the mission team to then reconstruct the trajectory data for us to the kind of accuracy that we needed to resolve the observations. But so it was a very intense time, but I'm now going to show you data from some of these orbits. Sorry, before I do that, let me just show you what the trajectory actually looked like. So all 22 of the orbits were extremely similar. They came in from above the northern hemisphere. They traveled down through the auroral field line currents. Inside of the rings, this red part of the trajectory here shows when we were in the highest measuring range. So that's when we were above 10,000 nanotesla. The circles that you can see are 3-hour intervals. So you can see how quickly we were moving through the closest approach period. And one of the things I'd like to point out here, and you'll actually see this in the data, is in the northern hemisphere, as we're coming down towards closest approach, we move through the auroral field line currents pretty fast. We don't spend much time in them at all. But on the outbound, as we're coming out through the southern hemisphere, we're actually skirting through the field line current region. And you'll see that in the data that I'm going to show. It's much more noisy. There's a lot more field line current signatures on the outbound pass. So before I show you the data, let me just remind you and myself what it was that we were actually observing. So there were 3 high latitude field line currents which we discovered at Saturn. And this was work done by Greg Hunt back in 2014 and 2015. The first system is the one shown in the top. This is the quasi-steady system, the one that you expect to see. The other 2 rotate with their respective hemispheres' planetary period oscillation period. And that gives rise to this PPO modulation that you see not only in the magnetic field data, but in other data sets as well. And these 3 systems are approximately co-located, and they then, the signals add or subtract from each other. And so this is what leads to the modulation of the field line currents. This leads to the overall B phi signature and position of it. just to set the scene for you before I show you the data, this shows you a typical grand finale orbit. This was one of the later revs. So we've got Z on the y-axis, and we've got rho along the x-axis, and you can see the closest approach. Where's my mouse gone? Here it is. Closest approach just inside of the rings. Now, these grand finale orbits, the duration was 6.5 days. The periapse distance ranged from 1.064 to just over 1.02, or down to 1.02 planetary radii. The latitude was close, the periapse latitude was close to 6 degrees south, and the periapse latitude was also confined to an hour either side of noon local time. And this shows you an overview of what the magnitude of the magnetic field in the top panel and the azimuthal component of the magnetic field in the bottom panel looked like on this particular Rev 291 from apoapsis to apoapsis. You can see in the top panel that all 4 of the measuring ranges on the instrument were used. So the first range goes up to 40 nanotesla, then we go to 400, and then we move up to 10,000 and above. And it was this top region here above 10,000, which was the region which we had used for the first time since the Earth swing by in 1998. And in this region, which can go up to 44,000 nanotesla, the digitization noise is 5.4. Now, looking down at the magnetodisk crossing, which I've pointed out in the top panel there, the lowest field we measured on this revolution was 1.74 nanotesla. That was during a magnetodisk crossing. The peak field, which you can see in the top panel, in fact, was not at closest approach, but it was in mid latitudes in the southern hemisphere. In the second figure below of B phi, you can see the value of B phi lies within plus or minus 50 nanotesla. So very small compared to the total magnitude of the field. And the various magnetospheric features are also shown in that figure. And these are the features which complicated the us being able to tease out the signal that was coming from the interior of the planet. So the auroral field line currents are marked. There's also a low latitude intra-D ring field line current. And I'm going to show both of these field line currents in the next plots for you. The crossing of the Enceladus flux tube is also shown down below here. And then last but not least, you can see the clear planetary period oscillations, which we saw in all of our data. And so really one of the reasons I wanted to show this figure here was just to underpin the fact we had to be really careful in our analysis and interpretation of the internal planetary field, because we really needed to remove the effects of these external fields before we could be sure about what was actually coming from the internal signal. So I've been saying to you, I'm going to show you the data. Let me now show you data from, these are the first 9 grand finale orbits. Just for ease of viewing, the ones that followed were extremely similar to this as well. So what we're looking at here, this is calibrated mag data from these first 9 orbits. We've got the radial component of the field on the left, the dipole component, the north-south component in the middle, and the B phi component on the right. The different colors are the different orbits. You can see how repeatable the observations from all of the different orbits are. And you can also see how much smaller the azimuthal component is compared to the radial and the theta component. And as I've already said, it's this B phi component, the azimuthal component, that will give us an understanding of any non-axis symmetry. So these are before I move on to the right-hand plot there, these dashed lines here show you the region when we were in the highest measuring range. And on the right-hand side in the B phi component, these are the field line currents as we were coming through the northern hemisphere and the ones that we saw in the southern hemisphere. You can see the ones as we're traversing down through the southern hemisphere are much more noisy because we spent a lot more time within that field-aligned current region. And so these are the two high latitude auroral field-aligned currents, but we made a new discovery, and that was right around closest approach. There was this new low latitude field-aligned current, which was confined to within the inner edge of the D ring. And we consistently saw that on all of the orbits. And if we could just insert that new field-aligned current into the meridional view, which I showed you earlier, it's this green, where's my mouse gone? It's this green region here, which was observed inside of the D ring. So based on the Grand Finale data, before we got that data set, this is how far we had been able to go as far as modeling the field was concerned. We had been able to model up to degree 3, but using the end of mission data, we had been able to go up to degree 11. This is for the axisymmetric part of the field, up to degree 11. Also shown on here, this dashed line shows you the 5 sigma uncertainty. We were able to push a little bit further. We tried to go to higher order moments. We went up to degrees 12, 13, and 14, which you can see down below here. But as you can see, they're not resolved. The values are below the uncertainty levels, but they're likely to be an order of magnitude smaller than the ones that we resolved up to degree 11. So as Hao alluded to earlier, we were able to use this data to get a better understanding of what we think was going on in the interior. And what we did is we used all 3 components of the data to really allow us to directly measure the offset of the magnetic field. And so this again is using the first 9 revs. Here we're plotting the data in a slightly different way. On the left-hand plot, we're showing a cylindrical radial component of the magnetic field with height above the magnetic equator. And you can see it's a very consistent feature, which is essentially telling us that it is offset north by 0.04663 planetary radii. But if you look closely here, you will see that there's a very small variation from orbit to orbit. It's not lying exactly on top of each other. And so we thought maybe we can actually use that variation to see if we can find any measure of non-axis symmetry. So if we do that, this figure here shows you the magnetic equator on the y-axis and the longitude around the planet on the x-axis. The dashed line shows you what it would look like if there was no tilt at all. The blue line shows you what the data should look like if we had a 1 degree tilt. That's what we would expect it to look like. If there was a 0.1 degree tilt, which is what the earlier data sets seem to be pointing at, the Pioneer and the Voyager data sets, we would expect our northward offset of the magnetic equator to lie along this red line that we can see here. But the data itself are the green circles. And you can see they're lying very close to the 0 line. But if you actually use that data, it allows you to work out that delta Z that you can see allows you to find out that actually the longitudinal variation of the magnetic equator along these Grand Finale orbits was less than 18 kilometers, which in the bottom right, I've just put a number to that. That's giving us a dipole tilt, which is less than 0.0095 degrees. Using this data, this shows a figure similar to what Hao showed earlier for Mercury. What we did is we examined the radial component of the magnetic field at 0.75 planetary radii. And this is the degree 4 to 11 contributions. And these correspond to a latitudinally banded structure. with a characteristic width similar to the off-equatorial zonal jets which have been observed in the atmosphere. And the rapid latitudinal variations in the field suggest the existence of a second shallow dynamo, which is maintained by the background field from the deep dynamo and the deep zonal flows in the semiconducting region closer to the surface. So this is evidence from the MAG data for deep differential rotation, which is consistent with work done by the gravity team. So let's then have a look at what our understanding from these grand finale orbits was. So this shows you a meridional view of the MAG observations. The magnetic field lines are the solid lines. Overlain on top of that is the trajectory of the spacecraft, which we've seen before, but you can see here. And we have inserted on that the size of the azimuthal component of the field along the trajectory. And it reveals, as I've marked in there, the high latitude auroral field line currents. It also shows you the low latitude interhemispherical field line current inside of the D ring around periaps here. And we've also labeled for you there the A, B, C, and D rings as well. And so what these grand finale observations confirm is the extreme level of axisymmetry of the internal field, with an implication for the presence of strong zonal flows or differential rotation and stable stratification surrounding the deep dynamo. And this is consistent with small-scale axisymmetric internal magnetic field structures originating in the shallow interior. And we've actually shown these in this layer here as field lines within the planet, and also shown as the tentative deep stable layer, and then the deeper dynamo layer overlying the central core. And those are all shown by different semicircles in the interior there. So what we wondered was whether we could actually push the data even further. So I've alluded a couple of times to the fact that there was this very complex nature of the magnetic field around closest approach, where in addition to the internal planetary field, we had the currents from the magnetosphere, which we can model pretty well, currents from the ionosphere, which because they were below the spacecraft appear to us as internal, but we can get an understanding of what their impact is. And then we were wondering whether we might be able to see an electromagnetic induction response from the interior. Now, this induction response we would expect to occur for sounding frequencies between 10 hours from the rotation rate and also the orbital frequency of the grand finale orbits, which was 6.5 days. And they would result or arise as a result of time variations in both the magnetospheric signatures and the ionospheric signatures as well. So based on our current understanding of Saturn's internal electrical conductivity profile, we would expect, this is work done by Hao and Dave Stevenson, we would expect the induction response to occur around about 0.87 planetary radii. So what we did is we removed the magnetodisk field and the internal field, so the Cassini 11 internal field model that I showed you earlier, and we then solved for the induced axial dipole moment. And what you can see from this figure here is it shows you that induced dipole as a function of the magnetodisk BZ field. We've done a best fit slope to that, and that corresponds to induction at a depth of 0.86 planetary radii. But as you can see, the uncertainty of that slope is huge. 1 sigma is 0.3782. So all we can do with this is make a consistency argument here. And that is that the electromagnetic induction response measured by these grand finale orbits is consistent with our current understanding of Saturn's interior electrical conductivity profile. So we thought, let's push this search for non-axisymmetry a little bit further and see what we can do. So I've already shown you that with the positions of the magnetic equator, that any level of departure from perfect axisymmetry is extremely small. But what we did, and this is work that Hao described in a paper from 2020, is we carried out a search for non-axisymmetric moments up to spherical harmonic degree and order 3. But we needed to keep in mind that since the internal rotation rate is uncertain, we needed to survey a range of rotation periods. And the survey we carried out was from, as you can see on these figures here, 10 hours, 30 minutes to 10 hours, 55. And these figures show in turn the dipole tilt, the relative non-axis symmetry in spherical harmonic degrees 2 and 3, and then along the bottom, the RMS residuals from this search as a function of the rotation rates that we searched through. And you can see there is no dominant peak can be identified, and the peak dipole tilt is at less than 0.07 degrees. So confirming, based on the other work that we did, that the internal field at Saturn is 1,000 times more axisymmetric than that which has been observed at the Earth and at Jupiter. And I will just quickly summarize, and then we can open it up for questions. So the observations from the end of mission orbits by Cassini revealed this low latitude field line current system inside the D ring, which hadn't been observed before, but then you wouldn't have expected us to because we hadn't ever gone to that region before. The magnetic dipole tilt is very small, less than 0.07 degrees. And the axisymmetric field, internal field, is complex and it's rich. It's got rich high degree content. Implications for this as far as the internal field is concerned is that we know there are some axisymmetric small scale magnetic structures beyond degree 9, and I have shown you evidence for that today. With the implication being there's a second shallow dynamo maintained by the background field from the deep dynamo, and there are some deep zonal flows in the conducting region somewhat closer to the surface. And I'm sure that's my last slide. I will stop sharing and open it up for questions.
Okay, thank you, Michele.
Of course, thank you.
So do we have questions for Michele? Krista?
Thanks, Michele, for the really interesting talk.
Thank
One
you.
of the New Frontier mission concepts that are proposed are a Saturn probe. What do you think you could expand on in terms of the magnetic and interior knowledge from an upcoming probe mission, if one is selected?
I would like us to maybe try and get a better longitudinal coverage at Saturn. Partly because all of the grand finale periapses were at noon local time, and I know the planet was rotating under us, but I do wonder how much of an impact being in sunlight had on the field line current observations that we saw. And so it would be really good to have some periapses at some other local time. I think that would really help us resolve better some of the internal structure.
Yeah, okay, thank you. Any more questions? Okay, if not, I'll ask you a question. So
Okay.
when you showed your the profile for the deep zonal flows, I don't know if you can go back on these, but they look quite different from the surface zonal flows.
Let me go back to sharing the screen, shall I? And you can. Oh. Sorry, can you remember? You shout which slide? Can you see my slide?
The previous slide.
Sorry,
The previous slide.
that one.
Yeah.
Yeah.
How does that compare to the surface flow?
I don't have anything with me that can show that. Off the top of my head, I can't remember a direct comparison. I can send something on to you. I don't know if anyone there has something that they can compare, but I don't have anything to hand that I can show you.
Johannes wants to comment.
Of course, go for it.
So I think this was in collaboration with the gravity team, right? And I remember the paper showing that this kind of zonal flow is consistent with the magnetic field and the gravity data, right?
That's right. Yes.
And for
yeah.
producing
There was a
BR,
follow-on
of course,
paper. Yeah. Sorry, there was a follow-on paper which
Yeah.
which showed it, including
by
gravity,
Caspi's
wasn't
group,
there?
right?
Yes. Yes.
Yeah.
That's right. Yeah.
And of course, to produce BR, which we could measure, you need an alpha effect, which was, assumed, somehow imposed, right?
Yes.
So
Yeah.
you produce the toroidal field by the zonal winds, but then you need an alpha to produce the BR. And that was shown to be consistent with your observations and with the gravity field, which I found quite remarkable.
Yes. This here was just based on the BR data. Yeah, but there was follow-on work which looked at both of them. That's correct. Yeah.
Okay, thank you, Michelle. Do we have any more questions or comments from the floor? No, if not, let's thanks Michelle again.
Thank you very much, and sorry I couldn't be there in person.
Okay, thank you. So we're going to break for lunch now, and